In this section, we're going to look at numerical techniques for locating a root of an equation. Consider the graph of y equals f of x below. We're interested in solving the equation f of x is equal to 0. The x-axis is the line y equals 0, so we're interested in the point where the curve crosses the x-axis. This gives us a root of our equation. So we can see there is a root here at x equals alpha. If we look to the left of the root, we can see the curve is above the x-axis. And if we now look to the right of the root, we can see the curve is below the x-axis. Let's look at this point A. A0 is a point to the left of the root. f of A is greater than 0. Remember, f of A is the value of f of x when x equals a. So this is the point with coordinates a, f of a. Now let's consider B. B0 is a point to the right of the root. f of B is less than 0. Remember that f of b is the value of f of x when x equals b. Since the curve is below the x-axis, it follows that f of b is less than 0. And this is the point with coordinates b, f of b. We can make use of this analysis to locate a root. If we find that f of a is greater than 0, then the curve is above the x-axis when x equals a. We can see that here. Here's a, and the curve is above the axis, which is shown by f of a being greater than 0. If we then find another point B, so that f of b is less than 0, then the curve is below the x-axis when x equals b. Provided the curve is continuous, and for these purposes consider a continuous curve to be one that you can draw without taking your pencil from the page, it must cross the x-axis in between. So we know there is a root between a and b. Consider this in really straightforward terms. We have a point here where we know the curve is above the x-axis, and a point here where we know the curve is below the x-axis. If the curve is continuous, you're going to draw the curve without taking your pencil from the page. It stands to reason that somewhere between a and b, you're going to have to cross the x-axis. And where you cross the x-axis is a root of the equation f of x equals 0. This clearly applies if the curve slopes the other way. If we find that f of a is less than 0, then the curve is below the x-axis when x equals a. If we find that f of b is greater than 0, then the curve is above the x-axis when x equals b. Clearly, if you were drawing the curve between a and b, and you could not take your pencil from the page, you'd have to cross the x-axis somewhere. So provided the curve is continuous, it must cross the x-axis in between, so we know there is a root of the equation f of x equals 0 between a and b. The point about continuity is important. Consider this curve, which might be something like y equals 1 over x. In order to draw this, you need to remove your pencil from the page to draw each arc. The curve is above the x-axis here and below the x-axis here, but we don't see it crossing the x-axis anywhere. This is because if there's a discontinuity, the curve can go off the top and come back in the bottom. Think of some other curves that do this, such as y equals tan x. A sketch can therefore be useful. You should know whether or not the curve is continuous before you apply this technique. Note that basic polynomials, such as quadratics, cubics, quartics, and so on, are always continuous. For example, consider y equals x squared minus x minus 4. Here's an accurate plot of this graph. We can see there is one root of x squared minus x minus 4 equals 0 between minus 2 and minus 1, and another between 2 and 3. Consider the table of values. Here we have some x values and some values of x squared minus x minus 4. If x is equal to minus 2, the function evaluates to give 2. If x is minus 1, it evaluates to give minus 2. At 0 it gives minus 4. At 1 it gives minus 4. At 2 it gives minus 2. And at 3 it gives 2. Note the change of sign here. The 2 indicates that the curve would be above the x-axis when x equals minus 2. The minus 2 indicates that the curve is below the x-axis when x equals minus 1. So this change of sign indicates there's a root in between, provided the curve is continuous. And the same is true here between 2 and 3. The minus 2 indicates that the curve is below the x-axis when x equals 2, and the 2 here indicates that the curve is above the x-axis when x equals 3, and therefore there's a root between 2 and 3. The question remains, why would we use a numerical technique? In the past, we've solved lots and lots of equations and never used a numerical technique. Some equations, however, cannot be solved algebraically. Consider x equals 2 sine x. There is no way of rearranging this equation so that we have x on its own. Other equations can be solved algebraically, but this solution may be very complex, e.g. a general cubic. Most of the cubics you've solved have worked out nicely because using the factor theorem enables you to find at least one of the factors. This is not always possible, and the questions that you've been given are worked out very carefully for you. A general cubic can be very difficult to solve. There is a cubic formula, just like there is a quadratic formula, but it's hugely more complex. If you don't believe me, look it up on the web. It's so complex that in practice, people would rather use a numerical technique rather than find the exact answer using the cubic formula. And of course, in practice, a numerical technique can give a solution to as many decimal places as we want. If we do not need an exact solution, Sometimes it's simply easier to use a numerical technique. In many ways, this is an insight as to how most real mathematics is done. Most of the equations that arise from physics, economics, and other areas cannot actually be solved, and very often in the real world, numerical techniques are applied to try to find roots of equations to as many decimal places as required.